Now, when two non-metals bond with each other, both of them want to have an extra electron because they have a high electronegativity. So they share their electrons. The two half-filled orbitals come together and they form a new molecular orbital, and that's where the electrons live. The electrons must have opposite spin. You remember that from Pauli's exclusion principle. The electronegativity difference is usually less than 1.7, but we tend to define it more across two nonmetals being the important defining factor. Once the two nonmetals have shared electrons, they become one unit and they become what is called a molecule. And covalently bonded substances cannot conduct electricity at all. Let's take a look at how water bonds. Okay, what you can see quite clearly here is that the water is, the oxygen has got 6 electrons, it would like to have 8. The hydrogen has got 1 and would like to have 2. This hydrogen has got 1 and it would like to have 2. So what they do is they come up with a little plan. They join together and they actually share electrons. The electrons get shared. They tend to spend more time at oxygen's house, but they get shared between the molecules and they form a molecular orbital. That is a covalent bond.
This tiny drop of water is really made of millions of tiny molecules, and those millions of molecules are made up of tiny atoms. Can you believe it? Amazing! It all starts with the atom. In their natural state, an electrically neutral atom has the same number of negatively charged electrons as it has positively charged protons. The protons are found in the nucleus, and the electrons are located around the nucleus. The electrons are distributed in shells. The first shell can hold 2 electrons, the second can hold 8, and the third can hold 18. The electrons in the most outer shell of a particular atom are called its valence electrons. Atoms react chemically and bond with other atoms with these valence electrons. Atoms are real control freaks. They're always trying to fill their shells. If an atom has 1 electron in its second shell, it will try to lose 1 electron or gain 7. And let me tell you, it is much easier to lose 1. With more than 3 valence electrons, it's easier to get electrons by sharing them with other atoms. Let's look at hydrogen. It's in the first group of the periodic table. It only has 1 electron in its outer shell, just like all the other elements in the same group, because elements in the same group have similar chemical and physical properties. All of these elements bond very easily with other elements that like to gain 1 electron. Hydrogen is a bit unusual, since it only needs 1 electron, not 7, to fill its shell. Hydrogen is happy to share an electron with another atom to fill its shell. Take our drop of water, for example. 1 water molecule is made up of 2 hydrogen atoms and 1 oxygen atom. The oxygen atom has 6 electrons in its outer shell, or a valence number of 6. It would love to gain 2 electrons. Each hydrogen atom has a valence number of 1. And when the 3 of them get together, they really bond. Behold, the water molecule.
So, what we're going to do now is we're going to draw alpha diagrams. We're actually not going to draw the alpha diagrams, they take too long. But we are going to draw Lewis dots and Cooper notations, and I'll show you about Cooper notation in a second for each of the following. Cooper notation involves a line representing the shared pair. So let's go with hydrogen. Hydrogen has 1 valence electron. The other electron is there. That hydrogen shares, and that hydrogen shares, and they both think that they are they've both got 2 electrons, and 1 line between them represents this 1 shared pair over there. If I now do hydrochloric acid, hydrogen has 1, chlorine has 7. Chlorine would like 1 more. Hydrogen would like 1 more. Hydrogen now thinks it's helium. Chlorine now thinks it's the chloride ion. So it's neon. So you land up with HCl. If I were to do chlorine, I would say this chlorine has got 7 valence electrons. This chlorine has got 7 valence electrons. So they share, and I land up with them, each thinking they're neon, and it's chlorine with a single line between them. Why? Because there's one shared pair over there. What if I did something like nitrogen? Nitrogen has got 1, 2, 3, 4, 5 valence electrons. The next nitrogen has got 1, 2, 3 of them are unpaired, so I just need to make them unpaired. Now they each want 3 extra electrons, so what happens is they borrow or share with that, and they share like that. As you can see, that's very untidy. So I'm going to draw it a little bit neater, and I'm going to say, I know that they're going to share 3 electrons, so I'm going to put those 3 electrons in the middle, like that, and we're going to say those were shared and those were shared. This nitrogen now thinks it's got 8. This nitrogen now thinks it's got 8. And therefore you land up with each of them sharing 3 electrons with the other one. So it's 3 electron pairs that are shared. You're going to need to draw things like ammonia, methane, and water. And we now need to, it says, consider the molecule's shape and polarity. I'm sure you can all agree that this is a straight line. It's called linear. This is a straight line, it's called linear. This is a straight line, it's called linear. This is a straight line, it's called linear. The electronegativity of hydrogen is 2,1 and 2,1. The electronegativity difference is 0. This is what is known as a non-polar covalent bond. Chlorine will do exactly the same thing. Nitrogen will do the same thing because they have the identical electronegativity. But hydrogen chloride is 2,1 and 3,5. That means that the chlorine side is slightly negative and the hydrogen side is slightly positive. We call that a polar covalent bond. I'm going to look at these ones now on the next slide. So if I have got nitrogen, it has 5 valence electrons. Hydrogens come along, they have 1 valence electron each. They share, they share, they share, they share. They do not have the identical electronegativity, so this side turns out to be slightly negative. There's also some extra electrons there, and the hydrogens are slightly positive, so it is a polar covalent bond. And we give this a special shape. It is called trigonal pyramidal. It's got like a little pyramid in its shape. If I look at methane, you've got carbon. The 4 electrons actually do something which is called hybridization. In other words, instead of staying as a pair, the one pair breaks up and becomes 2 lone electrons ready for bonding. In come the hydrogens. They each bring 1 extra electron with them. And you land up with a, if I draw that as a Cooper notation, notice 1 shared pair each way. By the way, the Cooper notation for the ammonia was this. There you go. And what happens is actually, although each of these little bonds is a little bit polar, overall this whole molecule is completely symmetrical, so it turns out to be a non-polar molecule. It's a bit of an exception, even though they are polar bonds. And this shape is called tetrahedral. Why? Because it's got 4 bits to it. 1, 2, 3, 4. That's called tetrahedral. The ammonia was trigonal pyramidal. So this is just a slightly neater version of them all. Let's just take a look. This would have been an Aufbau diagram. You can see they form a molecular orbital. With the hydrogen chloride, they form a molecular orbital. With the chlorines, those 2 electrons form a molecular orbital. They share electrons. It's a linear molecule, a linear molecule, a linear molecule. Non-polar, non-polar, but here there is an electronegativity difference, so it's polar. Looking at nitrogen, there's 3 molecular orbitals formed so that they can share 3 pairs of electrons, but it's still a non-polar molecule. Here's your pyramidal or your trigonal pyramidal with the one side being slightly negative and the other side being slightly positive, so it's polar. Polar just means that there isn't a balance in the charge. This is unbalanced in its charge. This is weird. Tetrahedral, carbon has 4 unpaired electrons, and it is called hybridizing when it unpairs those electrons like this. And these are polar bonds, but the molecule overall is nonpolar. Water, on the other hand, has got oxygen, which has a higher electronegativity than hydrogen. So it shares electrons with the hydrogen. The hydrogens become slightly positive. The oxygens become slightly negative. It's a polar molecule. The shape of this molecule is called angular. These are just some diagrams. That's what an angular molecule is going to look like. This is what a pyramidal molecule will look like. The big nitrogen with the little hydrogens, like feet of a poiky, if you like. And then this is your tetrahedral molecule where it is perfectly symmetrical.